Okay, so in this section, we're going to talk about network topologies as defined in the Dallinger network object class. What I want to start by saying is I want to say a little bit about what the purpose of networks are and how you should think about them. And I think a good place to start in thinking about this is the transmission chain. If you'll recall, in a transmission chain, just like in a children's game of telephone, information is passed down a chain from one person to the next. And in Dallinger's representation of a transmission chain, there are two components. There is the chain part of it, and there is the transmission part of it. And it separates these two things out. The chain, in a transmission chain, the underlying network structure is a linear chain where some source of information, like a hieroglyphic drawing or some story that somebody wrote, is transmitted to the first participant. And so that source of information is connected to the first participant in a directional link. The first participant is connected to the next one down the chain. The second participant is connected to the third, the third to the fourth, and so on. That network structure is distinct from the process that plays out over that network. And in the case of a transmission chain, the process that plays out over the network is the very first node in the chain transmits information to the next one, and it flows down the chain in that direction. And so what we're talking about here are not the processes that play out over networks. In many cases, your particular experiment will have some implied network structure and some implied process, and it will be your job to figure out what is the implied network structure and what is the implied flow of information in the design that you've been thinking about, and how do you then make that implied design explicit in Dallinger. But what we're going to be talking about here is the actual network structure. Who is capable of transmitting information to whom, even if they don't in the context of a particular experiment, because, say, one person decides not to share from somebody else, or in the case of, for example, a social learning experiment, though somebody could learn from anybody in the previous generation, per se, say they decide, because of something like a prestige bias, only to learn from particular others. Okay? So this is about network structure. So Dallinger networks determine the flow of information between participants. They do that jointly with the actual definition of how information is transmitted from agents to agents. So it determines it, but it actually it partly and jointly determines it with your definition of how information is transmitted from node to node. Participants can be in multiple networks sequentially, and they're represented by agent nodes. And so this is an important distinction that's come up a bunch of times before, which is that participants and agents live in different conceptual universes. A participant corresponds to a particular human in a particular context of an experiment. Typically speaking, in our Dallinger experiments, what a participant is a particular person in the context of that Dallinger experiment. Meaning that participants aren't exactly people, because the same person could be multiple participants in each of many different experiments. However, a participant can create multiple node objects, and in many of the designs that you'll create, a participant will create many nodes, each of those nodes belonging to some particular network. Those networks can contain different kinds of nodes. One of those kinds of nodes is a source. Sources only transmit data, but do not receive it. And they can also contain agents, which are people who can both transmit data and receive it. Yeah?
But one agent corresponds to one node always? One agent always corresponds to one node, or one agent can also have multiple?
Yeah, so an agent is a subclass of a node, and so each agent is a node. And is just one node. Connections between nodes in Dallinger are called vectors, and they can be unidirectional or bidirectional, meaning when A is linked to B, that could imply that also B is linked to A if it is bidirectional, or in the unidirectional case, when A is connected to B by a vector, that does not mean that B is connected to A. And importantly, those vectors can be marked as being failed if one of the nodes has been excluded. And so this is a way to This is a way to mark, usually for your own bookkeeping and for later recruitment and insertion of nodes into networks, where they can actually be linked up. Okay. So what I'm going to talk about is both network topologies that are baked into Dallinger, ones that you can just use without needing to write them on your own. And while we're going through those, I'm also going to point out some of the ways that those particular built-in networks are defined, because I think in many cases you'll want to write your own network structure. In practice, we've found that there's a kind of arms race between our development and people's use of Dallinger, which is as we create new capabilities and allow more complex network structures and experiment designs, people spend their time thinking about what interesting new experiment designs they can run, and so they have more and more complex use cases. What this means is that though you can do a lot of interesting studies with the built-in networks, for example, you can run all sorts of transmission chain experiments. Typically speaking, people knowing that it's pretty easy to run a transmission chain, think of, oh, what are interesting variants that we can run on this? And those often end up playing out in terms of writing your own network structure or writing your own process to play out over that network. Some of them are more useful than others. In fact, some of them we have basically never used, whereas others are used in maybe 20% of all Dallinger experiments that have been run. You can create your own network topologies, and what's important to say about the way that they're created is that they're created via specifying the network construction algorithm, with like one exception. But generally speaking, what happens is that you're always going to be answering the question, where do I put a new node when that participant's node has arrived to the scene? So here we are, we have a network, it exists, a new node is going to be added to it, where do we place it? That one exception is sometimes there's a pattern that people want to use where they know beforehand a very particular network structure. You'll see here that we have some experimenters who have used like a famous network structure called like Karate Club. It's just a particular social network that was found in I forgot if it's a children's or college karate club. And it's just a very particular small network. And rather than defining that as a construction algorithm of where to add each node when they arrive, instead what that experimenter did was to basically hard code the list of nodes and edges, and then to say, like, convert that into a network construction algorithm by saying, okay, we have a new node that's arrived. Which of these nodes in the hard-coded representation should they take on the role of, and then wire them up accordingly. So it's still a network construction algorithm. And you'll need to think about how to convert the experiment's network structure into some network construction algorithm. Okay. I think I've basically said this. What I'd like to show you is some of the actual common topologies. A very useful common topology is an empty network. So in an empty network, there are no vectors linking nodes. There are no connections between them. This network is only appropriate for a study where you don't actually need a source or to pass information between participants. And you can also use this as a base for a completely dynamic network by connecting nodes in your own code. So you could initialize a network as being empty, and then say there's something about the participant's behavior that's actually going to determine what the network structure looks like. Like, so for example, if you want to write a Dallinger experiment where what's happening in the experiment is that newcomers are shown some sort of interface and asked, where do you want to link yourself up to, or which of these other nodes do you want to connect with, or where do you want to place yourself? You could initialize the network as empty, and then on the fly add new nodes and new vectors between the existing nodes. Okay, so this is empty. It's the starting point.
Function that if you just want to put a connection, is there like a connect function?
It's in the JavaScript API, I can't remember. It's either add connection or add vector or something like that.
Yes, so there's a function that just does that.
Yeah, you can do it from JavaScript or you can do it from Python. There is a function called.
From JavaScript as well.
Yeah.
So this would be something that allowed you to create an experiment where not only was the network structure dynamic, but it was in some way controlled via user interactions. A second network topology is burst. Burst has a kind of hierarchical structure where there is some root central node that connects in a one-way connection to all the others. So one particular use case for this is when you have that central node be a source, so that you want a particular, for example, you want to seed a bunch of chains going outwards, and have the same source of information transmit to all of the participants. Or you could have a case where the first participant has a different task than the others. Like, for example, there's somebody who is going to actually determine, like in a kind of organizational, like psychology setting, or just studying management and organizations, you might have a manager who's deciding, how do I split work among a bunch of people, and you would have that first node be like a manager type who is going to receive a list of some work that needs to be delegated, and then they're connected to all of the people to whom they can delegate tasks. And critically, the subsequent nodes can't participate until the first node is complete, because these links are unidirectional.
So in the big lab, when the first child completes, and everyone else is done.
No, then
No,
you
it-
start.
Yeah, it's like once the parent has completed, the children can start, just like in a transmission chain where you seed it at the beginning, and then in this design you would likely then write recruitment logic, which says once the manager has completed the decision of how to delegate, recruit all of the delegates. Okay, so let's take a look at what this looks like under the hood. We start by defining burst as a subclass of network. It then has a docstring, a burst network. A burst network has a central node with an outgoing connection to each of the other nodes. You'll see that we define this polymorphic identity. This is what tells in the network table, this is what tells SQL Alchemy that it can instantiate this burst Python object by connecting it, by finding the corresponding row of type burst in the networks table. And then you'll see that the entire definition of the network is via this network construction algorithm of what do you do when a new node arrives. Okay, and so what you do in this particular case is first you look up and you find out how many, get this current set of all the nodes. If there is more than one of them, then figure out who that first node is by finding out who arrived first, and then connect that first node to the newcomer. Okay, and so in this network construction algorithm, if you are the first node, you're just added to the network and you aren't linked to anybody. So that's the manager who arrives and is just floating there as a single lone manager. And then each of the newcomers, as they arrive, they're not necessarily all going to get there at the same time, but as each of them arrive around that circle, they're each linked from the first node to them. Okay, so it's pretty simple in terms of as far as burst goes. This is just about the simplest that we have, where there's just one conditional logic that just determines what you do with the first node versus all subsequent nodes. Things can get much more complicated, but here's a no more complicated variant, which is a star network. A star network has a two-way connection between the manager and all of the delegates. This is what you might want in a case where it really is much more like the case of management, where not only are you going to delegate tasks to a manager, but you might want the results of those tasks to get passed back up to that central manager, who then might repeat the process in some way. If, for example, they were maybe checking consistency across the nodes that they had delegated things to. Okay, you could also use this to represent a moderator who can send messages to everybody, but where the users can only talk centrally to the moderator. Another built-in network topology is the chain. The chain, we've talked about this at length. Each node is connected to the one that follows it. Another quite common network that people use in all sorts of experiments are a fully connected network. This is where each node is connected to every other node. And so you can think of the network construction algorithm here as, it's also pretty simple, but because you don't know you don't have the full set of nodes available at the time that a newcomer arrives. Each newcomer only has available to it at that moment it and all of the ones that came before it. The network construction algorithm says when a newcomer arrives, link them bidirectionally to everybody who is currently there. And so you slowly grow a fully connected network node by node, where the first person arrives, they see who their neighbor, who the other available nodes are. There's nobody, so they stay put. The second one arrives, sees who all the available nodes are, finds that there's just the one person that came before them and creates a bidirectional connection with them. Third sees that there's two, creates bidirectional connections to the second and the first, and so on until you get at every moment you have a fully connected network of just size n plus 1.
But in the implementation, right, the fifth node doesn't guarantee that 4 is connected to 3. You just connect to everybody else.
Exactly, that's true.
So
Yes.
it becomes a fully connected network. But locally, it's just connecting to everybody that was before.
It's fully connected globally, but each newcomer, in this particular construction algorithm, each newcomer is responsible only for the links that they're a part of and do nothing to check whether, for example, in the meantime, somebody has broken a connection between.
That, and also what would happen, I mean, depending on how much time does it take to set up a newcomer to this network, what would happen if you have some concurrency problems? Some guy takes a long time to set up, builds a connection, and then some other guy doesn't have the time to consider this as a part of the network, and then you might have a missing connection depending on the...
Yeah, we've run into every concurrency issue that one might ever have, and had to address this head on, and you'll have to confirm whether this is true. But my understanding is we've set up the database in such a way that like these sorts of changes are atomic, so that if effectively if two people joined instantaneously, well, it's never actually instantaneously, but whoever joined first, they'll complete that transaction before the next starts, and so yes, exactly that concurrency problem can arise in principle, and we needed to adjust the ways that rows are added to the database so that when
there was a little bit of problem in previous versions of Dallinger that is very simple boss, I would say, but the Dallinger, it's really, really good. So I don't think you'll ever have a concurrency problem. The downside of that is that you have sometimes performance issues, because this has a cost on performance, and so the Dallinger database is slower than you would think, especially if you're running to around about 3K nodes. It's when you start having problems, and so it's not a huge size. It's a huge size. It's a good size for MTurk experiment, but it's not a huge size. And then there is a magic trick. You just make the server stronger, and magically
you use the cheat code that comes on the back of your credit card.
But the cost is not so big. If the experiment runs a couple of hours, it's really not a lot of money. Yes, you're talking about an experiment where their participant is playing for, say, 40 minutes, and there's hundreds of them, right? So you're going to pay them a lot of money anyhow. So the server cost is not going to be the main constraints for such a big experiment anyhow. And yeah, so you just do a performance M and the down performance, some elevated level of performance. And
Jesse, this appeared as a problem with Vale's experiment, right? Like in some of the experiments we've run more recently, we've had a design where there's simultaneous participation and like the need for synchronous participation across participants who are chatting with each other, basically. And in that case, we have a waiting room, so we may actually have 100 people who are basically they're all waiting for 99 people waiting for the 100th to arrive, and the moment the 100th arrive, we just dump everybody into the experiment and then build this network on the fly, so that we run into exactly that issue where, rather than the normal case where you're just recruiting people and as they arrive, one comes a second after the next, and because there's a second delay between them, there's no problem. We had instances where we had 100 people being dumped into like constructing the network on the fly. And
yeah, I think we had to explicitly lock the node table on add node to network to ensure that we would do one at a time, which, yeah, in principle, I think we thought the request level database transaction management would be enough, but in that case it wasn't. But yeah, we have, I think.
But what was it? But it still worked, or it didn't?
I think once we locked the node table on node addition, it did work.
And it didn't hit the latency. I mean, that locking didn't.
It degraded performance a bit more, and we have had recently someone who had some performance problems because of this. I think it's fair to say that this bit is evolving, and if you have a problem with it, you should definitely tell us, because we are trying to still find the right balance between how much contention we can tolerate and how much the slowdown is. But Jordan's right, that the waiting room is always the one that is the most difficult. So we've tried running it with hundreds up to, did we try 1,000 in the waiting room once? And that was slow because, I mean, it does take time to do this, and if you're doing it sequentially, then you have to wait for every one of them to finish. And the alternative is to kind of do as you were alluding to earlier, which is you can, well, Dallinger could, it doesn't at the moment, but it could have less of a guarantee about locking and solving the concurrency for you, and put some of that work onto you.
I think that's what you mentioned yesterday. What about redefining because this topology is more or less equivalent to a matrix, what about redefining a maximal size for this matrix and having it, you know, instantiated at the very beginning of the experiment, and then just populating it with however many people you have? Would that solve the? I mean, then you don't have to lock any thread. Then you just have to populate, you know, and then the ordering is irrelevant.
You still do need to lock it, because you need to make sure that you're not giving the same node to two people at once.
Yes, but this will only happen when you are actually assigning the ranking of the person.
But
Not
changing the table, the difficulty is changing the table. So like creating the whole line, or just changing 1/5 parameters in the line, it's the same, I think.
I think it would introduce more problems than it would solve, personally. But
Yeah, I mean, definitely.
All right, so let's go from these simple networks to more complex networks. As people are developing more and more experiments, we're adding to the pile of these, and these tend to be what actual experiments look like when you use the full capabilities of Dallinger. If you're using it for transmission chains, you may never have to touch some of these, but I mean, really, even in transmission chain experiments, often what people are doing is like it's actually pretty rare to run a transmission chain experiment where the underlying network is just a single chain. Often you have logic that says, oh, in fact, I want to think about this as 20 simultaneous chains that may be linked in a certain way, and so you very well may find yourself wanting to use some of these, or building off of them in some way. So one of these network structures is called a delayed chain, and this is meant to deal with the fact that if you create a hit with a single assignment, and then add an assignment to it, and then add an assignment to it, and then get past 9, Amazon Mechanical Turk will say, sorry, when you instantiated this, you did not tell me that you were going to be creating more than 9, and so I didn't know to charge you a higher commission rate. And so now, rather than just retroactively charge you the higher commission, I'm just not going to allow you to add a 10th person. It's not how I would have implemented it if I were Mechanical Turk. I would just have retroactively charged the higher commission, but that's what they did, and so we needed a bit of a workaround. And so what we do is it ends up being a chain, but it is instantiated with enough independent nodes at the start in order to actually basically have Mechanical Turk know that this is what's happening. And so we've called it a delayed chain.
what happens with the nodes on the top? Do they get integrated into the same? Or are they just placeholders that will never get populated?
People will fill them with agents and they will do the task, but because they have been given the same data as the first node in the chain, it's not possible to integrate them into one long one because you've got 10 people who are given the same
wasted money.
Yeah, effectively.
But a lot of the time you would choose a different solution, which is to be running in parallel multiple chains. That resolves the problem in a different way. And then if you have typically like 50 people starting at the same time, you start with recruiting 20 people and just rotate those.
Sorry, is this just making 10 chains in parallel? Like,
what it's doing is it's creating this is when you want to create a single really long chain, but you don't want to create many really long chains. You just want one really long chain.
I see.
Somebody's wanted this in the past. And there, it's basically what you're saying is, I'm going to recruit 10 people right now, and they're all going to do the same task. I'm just going to pick whoever finishes first, basically, and now all the new nodes that arrive are just going to be a chain off of them, as opposed to off of any of the others. And so what that allows you to do is you can now create an infinitely long chain. You could, if you want, have a chain of 1,000 people, and Mechanical Turk will be fine with it because you've already instantiated the hit with above the limit.
Suppose you did want like 10 parallel chains though, how would you go about implementing that?
Yeah, well, we have two of the world's experts on that here who have created as many parallel chains, transmission chains.
So I've created my own objects and failed yet to integrate it with Dallinger, but I'd love to share it and we can share it. It's a little bit depending on the interpretation and the kind of setup that you have, and it goes to like deep theory of exactly what kind of expectation you have from the chain convergence. But we were thinking we don't really care so much about which person is playing what chain. We're just gonna run a lot of parallel people and let whoever comes join the chain, as long as they don't join the same chain twice.
Yeah,
that will just generate a mixture of stuff, which is good for some things. And so that, for example, will be a little bit dependent on the order of the participation. So what we did is just a bunch of people come, it doesn't matter how many, more than 11, just because otherwise you get stuck. And so usually typically we take 20 people, we put them in this side, and then we have as much as we want chains. And then every time that the new participant comes, he joins a chain, create an info, and we continue. There's only one little complication is, imagine that one person joins a chain. There's some way in which that person another person is not supposed to join the chain as well. So there are several ways to do it. And the way we have chosen is to have an indication of an open or closed network. It's going to be a state of the network. And once you just join the network, you close the network. And as long as you've ended the participation, you reopen the network. There's one little issue there is that you might have like somebody just starting a network, joining the network, and then just wait forever, and just closing his computer. Then that chain is going to be closed for a while. So then we decided that we would just wait for an hour to pass. That person is going to be kicked out of the network, and then in the attention check or data check or whatever of those, we're going to just prune the network, and that.
When you say many parallel chains, you mean specifically many instances of the class chain and then Amazon?
No, actually, it's all our own. We extend networks. So
it's a single topology, but it is equivalent to having 20 chains.
It's just we could have reused some of the chain thing, but by the time that I did it, there was not a chain didn't exist in the way that it exists now. But it's just an implementation of that class.
If I was going to do that same thing using the things that we've learned in this workshop, what I would do is at the very top of the board there, next to backend, we have setup calls create network. Create network, I would have returning a chain object that was each individual chain would be one of those. And in setup, I would change the default behavior from just instantiate one of them to instantiate however many. And then in get network for participant, I would have the logic of where do I put somebody. And that's glossing over a lot of the practicalities that you have to deal with, but that is how I would generally approach something like this.
Which is fairly what I think we're doing, except that we didn't, like you're not using chain, but we're implementing everything that was there.
Then how does Amazon know that you have enough? I didn't quite follow that.
What?
How does Amazon know that you have enough?
Well, the thing is that you recruit, say, 20 people, and what happens is these people, whenever there's a person finishing, you can recruit another one. So you keep a pool of 20 people. This is number of participant recruiting until you get to the very end where everything is filled, and then you somehow tell the network to stop recruiting. In the very end, you can be sophisticated and kind of predict how many left nodes there are, and this is what you were doing, but this is like just a trick. You can just having more participants and let them not do as much as you can. In the very end, in this topology, if you have like a network and you have like a lot of networks, in the end, you just need a participant to participant in just a very few of them. You still don't need a new participant because you don't want to the same participant participate twice. But just imagine that there's each participant is typically participant in 100 chains, but there's only 5 chains left. So you need a participant like that, and then another participant just to finish the last 3. And so in the very end, you kind of play them less. But
Okay, the next network structure that I'm going to talk about is the discrete generational network. If you're familiar with population genetics, this is basically a cultural variant of a Wright-Fisher process. So in this network, nodes are arranged into generations, and it has a few parameters. One of them is the number of generations, and the second is how many nodes there are in a generation. And what's going to happen is that remember, this is just about the network structure. And so in practice, this is used in the context of experiments where you want to study something like the evolution of social learning, or something where some group is going to learn from or do something that's contingent upon what a previous group or generation in the experiment did. But here we're just talking about what the network construction algorithm looks like itself. And so the first, let's say like the number of nodes in a generation is, we'll call it n. So the first n participants are each arranged into without any particular connections. They're just like the first n are effectively an empty, not an empty network, but a fully disconnected network. When that generation completes, a newcomer arrives, and that newcomer is going to be assigned to the next generation. And the question is, who do they link to? And in the discrete generational network construction algorithm, there is a fitness function. And that fitness function can be whatever you want and is basically always experiment specific, what the concept of fitness means in this particular experiment. But that fitness function determines how the newcomer links up to the previous generation. And let me just give you a couple of examples of things that we've done. One kind of thing we've done is to have the first generation of nodes each be performing some basic perceptual task where they're either right or wrong, and then have the next generation link up to them with probability proportional to either whether they're right or what percentage of tasks they got correct. So that's some node of fitness that's dependent on performance on the task. In another case, you may, Tom Morgan has run studies on something called the prestige bias, which is the tendency of people to prefer to learn from and defer to those who have higher prestige, those who more other people defer to. And so there you might have your fitness function be something like to encode a prestige bias, you may say you're going to be more likely to link up to people who many people from your current generation are currently linked up to. So that, for example, if in your current generation, half of them are linked up to one person and only a quarter are linked up to another, prefer to link up to the one who has more connections currently. You could also think about this in the context of like that would be similar to like the network construction algorithm that underlies a ScaleFree network, which we'll see in a second, where like in the Barabasi-Albert model, a newcomer arrives and connects with existing nodes with probability proportional to the number of connections they already have. So that would be another way to use this. But the idea is that each newcomer links up to some number of members up from the previous generation with probability proportional to their fitness at however you define it. Yeah.
What happens if, I don't know if this is a meaningful example, but if you only want to choose among less than 10 nodes, and you still want to develop more than 10 nodes, like this same problem with the delayed chain, but in this context. Would you have to initialize with 11 and start
so
9? Or?
I think by default, if you did this, then the extra ones that you recruited would go straight to the questionnaire because there wouldn't yet be a space for them in the network.
That's
so
interesting.
You might have to do something like we did with the chain. But I don't think anyone has needed that yet.
Yeah, and in practice, we've just initialized generations with 10 or more people. But yeah, if you wanted like a council of 4 people, and then yeah, you'd have to. Yeah.
So what you can tell people is that sometimes they will have, like you're telling the expected number of questions you're going to see. The 7 number of tasks is 100, but sometimes you'll see less than that. If that is the case, that means that you don't get.
I was wondering how would you implement that?
In practice, either just create a single network with more than 10, or the more likely case is if you actually wanted to run, you just wanted generational structures with 4 people per generation. Typically in your experiment, you're not going to just run one of those ever. Instead, you might have multiple experimental conditions, you might have multiple iterations, and you would just run those in parallel. And so because like the relevant question for the Mechanical Turk recruiter is not the number of people in a network that are joining at the same time. It's across all of your networks. How many people are you recruiting in that first batch? And so if you have 4 nodes in each of the first generations of networks and have at least 3 networks, then you could just recruit the full batch of 12 or more of them and be fine.
If I may as well. If we think back to the iterated drawing and the Bartlett demos we looked at yesterday, we could change the network there to be from a transmission chain to discrete generational and define the fitness function, and then that could be quite interesting. So for example, we could have 5 people each drawing that initial version of the owl, and then the fitness function is who's closest. And then that is the one that is given to the next 5 people. So you can also use this kind of thing as a way of steering an experiment by having a fitness function that prefers a type of result, and have multiple people and you pick whichever one is closest to what you wanted and see how that evolves.
Great, thanks. The next network I'll talk about is the ScaleFree Network. This is the Barabasi-Albert model of ScaleFree networks. It's defined by 2 parameters, m sub 0 and m. The first one is the initial number of nodes. They're fully connected between each other. The second parameter is the number of connections that each newcomer has. And the way that this algorithm works is that each newcomer after the first m sub 0 of them make m connections to those who exist, sampling the newcomers with probability proportional to their current number of connections. And what's interesting about this is, so like if you just play this forward in your head, let's say you start with 3 fully connected nodes and each newcomer is going to link to 2. Well, the first newcomer, the first after the first 3, like the 4th, looks at the first 3 and says, each of the first 3 have 2 connections, so I'm just going to sample 2 of them uniformly. But now, and then link to them. But now you have an imbalance among those 4. 2 of them have 2 connections and 2 of them have 3 connections. And so now when the 5th person arrives, they're more likely to sample the ones who have 3 connections over the ones who have two connections. And so what you get is this sort of rich get richer scheme that results in a kind of hub and spoke model where certain nodes have a huge proportion of the connections, and there are many more nodes that have many fewer connections. And you may have seen this before, but that's a scale-free distribution of nodes. Okay. Next up, I'll talk about the Sequential MicroSociety. This is a very particular experimental design, but one that's often used in studies of cultural evolution. And basically what you're doing is you have this kind of core society, and you're going to be linking up newcomers and then having older people leave. And so you have this kind of society that's always there and going to be connected to each other, but it's being replenished and people are leaving. And so you get this kind of it's called a sequential microsociety, and people use that to study models of cultural evolution where people are learning not from the ground truth of the world, but learning from an existing society or culture of people. Okay, yeah, I'd be interested to know if anybody ends up using this in that. People have used this in a few particular experiments. It's particularly if you're studying cultural evolution where that's most useful. Another network that's been developed is the split sample network. And this is interesting because this is an example of trying to think about the network structure implied in existing experiment designs. And so here what you're doing is like randomly assigning people to groups and conditions. In particular, what you can do is like before, how do I describe this? One method of analysis is to randomly assign your data to either exploratory or confirmatory analyses. This is like a split sample design. You then run your exploratory analyses on the exploratory set, decide what your analysis is, and never looking at the confirmatory analysis sample until you then nail it down and do it. This is in place of collecting some data, doing an exploratory analysis, collecting more data, and then running a confirmatory analysis. What's nice about this is that because you collected them both at once and randomly assigned participants or networks to your exploratory or confirmatory set, you can have greater confidence that there are no meaningful differences between your confirmatory and your exploratory and confirmatory networks. And so there's a few researchers who have used this particular design when they didn't know exactly how they were going to analyze the data at the beginning, and wanted to assign entire networks to the confirmatory sample or the exploratory or confirmatory sample. Okay, then we have some user-defined networks, the point being that we are all free to create our own network definitions that are either generic or for our particular experimental designs. In fact, some of these that are built in actually were built for that purpose, where somebody just, somebody had a need for us, like the split sample design or a sequential microsociety and built it. But there's several of them that are really kind of specific to particular experiments or experimental designs. And so here are some examples of those. One of them is the Karate Club network, which I mentioned. This is an undirected, unweighted network that shows connections between 34 members of Zachary's Karate Club. It's a famous network from a particular paper on, it's called an information flow model for conflict and fission in small groups from the Journal of Anthropological Research. I don't remember whether Zachary is a little kid. For some reason, I think he might have been somebody in like a college karate club, but I don't totally remember.
If he's the first author, he's probably not a little kid.
But he may have been modeling his karate club from childhood.
Yeah, okay, that makes sense.
And so you'll see that this network is basically hard coded here. It's a where what we've done is actually. Can one of you describe this?
Yeah, maybe.
I just
I think there might
like
be some stuff in the notes on the screen.
So
yeah. So
if you can read the, I don't know if you can see the topology definition over there, it's a long list of tuples that define pairs of node IDs, I think, or participant IDs, probably node IDs.
no, it is.
Or node indexes in the set, because
Yeah.
That's true.
The thing to note is that like Karate Club is not a subclass of network like everything else we've seen is. This is a special way to handle things where what you subclass is topology, and then this topology is just a hard-coded list of the actual nodes.
So the experimenter here wrote a subclass of network that they called topology, and the algorithm in that network checks the all edges list and says, okay, I am the 5th node in the set. Find all of the mentions of 5 in all edges, and those are the other nodes in the set I need to connect to. So the reason I didn't include the topology code in this is because it is quite long and quite complex, but the code is there. If you are interested, you can go and find it on GitHub. But this is, as Jordan says earlier, a way of encoding a static structure and making it readable compared to writing a Python function that tries to encode the static structure as
But it wouldn't necessarily be a very difficult thing to write. Just that particular case is a complex topology, a complex stuff. But like, if you just include that, right, you could easily write like you add node to network, look at that, see who is connected, and connect.
Yeah.
It's going to be a few lines of code, like just to implement something that does that. It's not difficult at all.
If you were doing this, I would recommend you do look at that code, because Ben has put a lot of work into making sure that it's robust against all things that could possibly happen, and it will handle big sets of data. So it would probably be worth your while if you wanted to do something similar to not start from scratch. But yes,
Is the idea that it's a way of expressing more complicated network structures, like list of tuples?
It's, well, in particular with Karate Club, there's no, like, the only known network construction algorithm for the Karate Club, because we don't know the, like, underlying psychological process by which Zachary's friends linked up to other friends, is to, like, look at the hard-coded list of nodes and find your role in it and link up to the ones in this list.
Yeah, what I mean is, like, I thought that is it literally just meant to instantiate that exact Karate Club?
Yes.
Because I was thinking
Yes.
that if you have a list of those things, you could instantiate any given
Yes.
random network.
Yeah. Basically, you could pre-generate any network
Yeah.
you wanted that didn't depend on any static network that wasn't going to depend on nodes' decisions.
Yeah.
Encode it like that, and then use that
And then-
instead.
and there are like 20 other examples in that file as
Right.
well.
I see. Okay.
So this is helpful, especially if you're trying to reproduce something that someone else has done, I guess, because if they had a very specific network that they documented and then they documented what happened,
Mhm.
you could say, well, okay, well, I'll reproduce that same network with new people and see what happens.
Mhm.
I was wondering, to me it was a surprise to say that topology extends node network and not the opposite. Because I think it was the first example, you had this line where the newcomers choose defined as the oldest node that was stored to the database. But here you can select them by index. To me it would be way more straightforward to do it so than by date. So I was wondering if both ways of selecting a node are possible in a topology or in a network, and why would you prefer one over the other?
So specifically, topology is somebody's custom network, and it's not part of Dallinger itself. If you were doing a chain of 10,000 people, it would be really inconvenient to do it like this, because you'd have to have 10,000 tuples that are just sequential numbers, and you cannot, in general, have an open-ended algorithm as a specific list of edges, but you can encode an algorithm that just delegates to a specific list of edges, which is why network is at the most basic structure and topologies that can go on top of that. And I think we'd probably be open to having topology move into the default set of networks available if people do find this easier, but as far as I know, it's only Vale Gates who has done this so far.
I don't think topology, I actually did topology, and I don't think it is a subclass of network.
I checked, it was.
Oh, okay.
Well, I think I checked.
Okay. Next one up is paired. In the paired network, it's actually lots of little networks. It's for like dyadic experiments where you want to have two people who are linked to each other, but to nobody else. So these are nodes have bidirectional connections to one other node. If there's an odd number of nodes, the one without a friend just sits there. And failed nodes are not replaced because these are meant for experiments where you're going back and forth and having interaction with another person, and if that other person fails, it doesn't really make sense to just have another person fill in with you in some dyadic. That would just be, you just get a new dyad instead. And here you can see the definition of it. It starts by defining the class paired as a subclass of network. It defines that polymorphic identity. And then it defines the network construction algorithm via the add node. What do you do when a new node arrives to the network? You find all the nodes. You get all the nodes that aren't this one. You find all of the available nodes, which are all of the nodes that don't have any failed connections. If
Do not have any connection.
Any connection whatsoever.
Do not have any.
So n.vectors vectors is by default is all the connections,
right.
And failed equals all means also includes failed connections.
Yeah, so that's very important. Yeah. This is basically find somebody who doesn't have any partners and who never had any partners. So then if there is anybody who does not currently and never has had a partner, choose randomly among them and connect in both directions to them. Thank you.
So what is the policy with timeouts here? If unfortunately there is, at the end someone left,
Yeah.
This if expression is evaluated, and what is the else? Yeah. What happens if there are not available nodes?
Oh, you're just left floating. Yeah, you do not have a partner.
You don't get any pay.
Well, this.
So this is the topology of the network, not the behavior of the network. So you could have your experiment could say, okay, well, if you are paired with anyone, we're going to just skip you to the.
So this is a responsibility of the.
Yeah, because it could be that you would have a network where it makes sense for one person to try and do something on their own. Maybe that would be valuable, but that is, as Jordan says, goes back to the split between the transmission and the transmission chain. This makes sure that people are paired up if at all possible. But anything that goes wrong with that pairing up is kind of left to the experiment.
Okay, here's another very particular kind of network. This is called Mafia Network. This is particularly for a game that is, depending on, it's some places it's called the Werewolf game, sometimes it's called the Mafia game. I'll just describe the game briefly because that'll make sense. It'll help make sense of what this is. You could play it in a group very much like this one. And basically what you do is you pick somebody who's going to be the kind of like grandmaster of the game. And we'd all have our heads down and they would assign us roles. And those roles, I'll use the context of the Mafia, those roles would either be like innocent bystander public or the Mafia. And critically, there are many fewer in the Mafia than in the general public. And also critically, there's an asymmetry in terms of to what extent they're informed about each other's status. If you're in the public, you know nothing about other people's group membership, whereas if you're in the Mafia, you have full knowledge of everybody's group membership, which is to say, if you're in the public, you don't know whether the people surrounding you are in the public or in the Mafia. And if you're in the Mafia, you know exactly for every person whether they are in the public or in the Mafia. The game then plays out in a series of rounds, night and day. During the day, the group, like everybody together, discusses who to vote off the island, who they're going to
kill?
In prison.
In prison, yeah, something like that. At night, everybody puts their heads down and closes their eyes. The narrator, the moderator, says, okay, Mafia, arise. They then silently look around the room and can communicate with each other, not vocally because they wouldn't want the public to hear. And they decide who to kill off. That person is then, like, they heads down, everybody's heads up. The person is told who's been killed off, and you proceed. And so you proceed in a series of rounds where the groups also have different goals. If you're in the public, your goal is to determine who's in the Mafia and like arrest them all, or whatever it is. And if you're in the Mafia, your goal is to kill all of the public. The game is amazing. It's probably, I think, the best example of complex social behavior that I've ever seen in any like arranged interaction. It's worth playing if you haven't before, and also if you have any interest in like social reasoning or judgment or decision making. It's a very interesting area to even try to start modeling, because it involves recursive reasoning about other people's partial knowledge, and it's good. Okay, and so this is an example where that game implies a certain network structure. That network structure is dynamic, so we can just think about it in that, like, you can ask, like, who is able to take what sorts of actions with respect to whom, and who can see whose identity, and that defines a certain network structure. So here we have a Mafia network. It's a subclass of network, and it says a Mafia network that switches between fully connected for all and only Mafia nodes. So that's like during the day, everybody can talk to everybody else, and so it's fully connected for everybody. We're talking about just about the communication network. During the day, anybody can talk to anybody, and so it's a fully connected network among everybody, public and Mafia. At night, though, all of the public are disconnected from each other. They're just lone nodes, and the Mafia remain connected with each other. And so, like this says, if you are a node that's of type mafioso, then first get all the others who are the mafiosos and connect bidirectionally just to them. So this is the connecting just the subset of them at night. And so you might switch between this Mafia network and a fully connected network night and day in order to like have these kind of two simultaneous networks that define which kinds of communication you ought to have.
The vectors of a flavor. You can flavor the vectors, right?
Yeah.
And then connect them with a flavored vector, and then we'll generate two types of networks.
Yeah.
And then when you do the actual searching, who's connected to whom, or transmitting and all of that, you ask, you basically, oh, that's going to be a lot of work.
So for most of these complex things, there's always going to be like 3 or 4 different ways of implementing it.
Mm-hmm.
This is just the way I do it.
So you actually, in this case, will just go and every now and then replace all the connections rather than having all the connections in.
I think that's how this one works, but I have not run this experiment myself. I don't know for sure.
But conceptually, how would you go about solving something like that?
Yeah, so you could do that. So you could get rid of all the connections and reconnect them using the networks. Another way you could do it is to have 2 simultaneous networks, a fully connected and a Mafia network, and depending on the phase of the game, change which agent is sending the info. But every participant would have simultaneously a day agent and a night agent.
Oh, that's
one way
nice.
of doing it.
And would you be able to send a note to the questionnaire if they die, or does it finish when everybody finishes?
I guess you would have to send that in some way. Probably, off the top of my head, I would probably do that in a fully connected day network by sending a death info. So I'd have a custom info for voting who's going to be imprisoned, a custom info for voting who's going to be killed, and a custom info for who has been killed. And then probably transform on all of the and a custom one for who has been imprisoned, and then have a transform to aggregate all of those infos to determine who was the winner of the vote and create the actual death or imprisonment on the server side. It's an interesting thing. It's definitely, you would have to do work to implement the entire game this way. But this particular example is just that idea of having two types of agent, one set who's fully connected, one that isn't, is again sort of conceptually separate from the idea of implementing the entire game in Dallinger. You could use this as a way of saying, okay, well, some of the users have access to collaborate and others don't, and there's multiple experiments that you could model with that network topology other than just the game of Mafia.
I think I actually got the base definition of the game wrong. I think the standard way to play it is that during the day, the public decides who to indict, and then the narrator or like the moderator tells you whether or not, like, informs the public about like the outcome of the trial.
And also, you didn't describe that there's one person who opens an eye and see who is like who knows who is sometimes called the watchman or something like that, and he has the capacity to see who are the mafia.
That's an optional character, and there are maybe 20 of those.
Yeah, there's lots. There's one who his goal is to get killed during the day, and if he gets killed, he's a fool. If he gets killed, everyone else loses.
Okay. Choosing the last thing here is about choosing a network. The iterated drawing demo uses a chain network, and so there's just a few discussion points, which include like what other networks might be interesting to use in place of a chain network, what could possibly be tested by changing only the network, and what could be tested if the experiment were altered to allow more than one drawing as an input. And so the point here is just like get you thinking about the network structures implied by the kinds of experiments that you have or might run, and what you might be able to do by thinking of the flexibility afforded by manipulating the network structure.
I think that somehow the kind of networks that you're describing, that you were asking, I think it's a point like there's a kind of class of a network like we're trying parallel chains, multiple participants, and then within participant chains where like you just do the same experiment but they join one by one and do the networks one by one. That's probably should be integrated into mainstream Dallinger because it's a very kind of standard use cases, and I think it's pretty much consistent across iterated learning experiment of a particular kind. We're talking about something that we'll talk tomorrow morning, but maybe it should be actually integrated in that array. This is something you might just want to do.
So, question about the iterated drawing / bottlet demo. So that is using chains, the chain network type. And suppose you wanted 10 chains of 10 people each. The way that it would do it is that it would just make one chain and get one person, and then when that person was done, it would get the next one, and so on. Like it builds up the chains. I see. So
whereas for me, it's a bit limited in the sense of bandwidth, because like we're talking about chains of hundreds of people. Mm-hmm. And another thing is like, yeah, you also want the person to participate in like multiple trials. So that both constraints, I think. I mean, that's very conceptually very clean, but just practically speaking.
I don't think so. When you just asked that question, you're saying that let's say you have 10 chains being run in parallel. Do you recruit one person to start, and then when that person finishes, recruit one additional person to fill the second? Typically, what you do is you just define in the experiment class. You would define the initial recruitment as being 10 people. Mm-hmm. And so now you recruit 10 people simultaneously. Mm-hmm. If you have 10 chains simultaneously, you can't have 11 people working simultaneously because... and so if you just set the initial recruitment to 10, it'll go 10 times faster because as soon as one of them finish, you'll automatically recruit another one, and now you can run it. It'll the amount of time it takes is linear, not in the number of chains, but linear in the number of
steps.
Yeah.
Okay, I see. All right. Well, that's...
so if you just because each of the chain will recruit one.
Yeah.
But if you have,
you must already do this.
we're doing now because our participants.
Well, unless you just have a person jump from chain to chain
That's
to chain.
that's
Yeah.
and then adds another complexity.
So
But it's not complicated. Like, it ends up in end network being like 30 lines, right? It's like the full. That's it, and the rest is.
So yeah, there are two ways you can do this. You can either do this as a network that models multiple chains as one network, in which case you would customize the add node method of that network to have the logic, or you could have it as multiple chain networks, and you would customize get node for participant to have the logic of how you assign a person between them. And there is a lot of flexibility, but as you said, that the more you get into the practicalities of an in-depth large-scale experiment, the more you have to make these decisions that are to getting your exact goals right. And you have a lot of trade-offs about things like, well, what happens if somebody is doing it more slowly than another? Because if you've got 10 chains and 10 people, and one person's being really slow and the other 9 have finished and are waiting, then do you actually make them wait, or do you tell someone, oh, we don't have any work for you now, and then you've only got 9 simultaneous? There's that kind of problem, and then there's the problems of making sure that you don't want people to be in the same position in the chain every time. You don't always want the same person to be the person who's first, because they might be really bad at it, and if they're really bad at it, it's going to change everything else. And these are all things that Dallinger doesn't really like making decisions for you about. You can follow this method and build up something that works, and then you try it and you go, actually, I want to change the subtleties here, and that's the kind of stuff that Nori has been working on. Like, he's got the experience of actually making it work with, is it 5,000 people or?
Over 100 at the 100 scale each time. I mean, overall there's a lot of people, but in each experiment is about 100. I think you get stuck if you are trying to generate networks of the size of like about 10 kilo nodes. That's about the limit.
Yeah.
But also, this limit is, there's also a limit about recruiting in simultaneous participant in MTurk. It's another thing that I was supposed to that I mentioned in the talk, but is you imagine that the MTurk community is infinite, but it's not. It seems infinite in the beginning, but there's actually about 1,000 people, I would say. You can get like 2,000 people, but you cannot, if you just try to recruit everybody. To correct me, other people have also a lot of experience in just MTurk in general, but my experience is like, if you want to recruit simultaneous participant, or not simultaneous, but just like a lot of people, it's actually not trivial to recruit more than about 1,000, maybe 2,000 participants.
It depends on your qualifications. Like if you say it has to be 95% plus with the 500 hits that they've done, then I would completely agree with you. There's also papers saying that like the total active MTurk community is about 7,000.
Yes, so that's the other
6
thing.
months every.
But it's changing. So yeah.
In that case, you're gonna have problems with duplicates, people taking the same. And then
so if it's one task, usually the task that defines that you cannot participate in one task. So that's what I'm saying. I want to get 1,000 people for that particular task. Either you do it with qualification and avoiding repetition, or just in one task. Then that task is not going to be. It's going to be difficult to populate that. And it's very easy if you get 400, but it's becoming increasingly difficult if you want towards 2,000. And if you want unique participants over a week, you can get to the whole cohort, which is about 7,000. You can get like getting there, but if then your experiment just doesn't accept you to repeating participants, you'll have to wait a couple of months to get another 7,000.
I have a question about qualifications. Actually, do you all normally do like the 95% plus 500 hits thing, or?
I don't do 500 hits unless it's default in Dallinger that I don't know about it.
Okay. I was just wondering. What
and the default is 95. And actually, I don't think that's really important.
I completely agree, but some reviewers can get upset about these things.
And
I was just wondering.
there's other. it's getting into a different talk, so we'll maybe take it offline. But basically, I think the right way to do it, also tackle with reviewers as well as bots and all of this, is to have a screening task that just do something that is not trivial for bots. A lot of the people who runs bots, whenever the task is gonna be more difficult for them to figure out, they just go to another person who is less concerned about it. So because a lot of the tasks in MTurk is just the API and the API, it's very difficult to do something like a screening task. Or then you just put this little screening task, and it just blocks, and it blocks all the free riders, and that's it. And the way to do it is to define in Dallinger, you're very incentivized to put everything in the bonus, because you can have all the sophisticated things, and you get also very reliable bonus payments. So people don't like the bonus because they think, oh, this recruiter will wait for 2 days before you initiate the bonus. But it's only since they see that right 5 minutes after you run the task, immediately, automatically you got that. It's a repeated game. They communicate within themselves. There's a repeated participants as well, if you don't force them. So they actually realize very soon that you're paying bonus in a very systematic way, and then they're totally happy to get everything in bonus. So then you reduce the payment to 10 cents, literally. And then all the free riders and bots, we should set a new task. Immediately in the beginning, you get all of them. They all just come to you. And then you pay them overall $5, and you got 50 of those for 10 cents. So $5, 50 cents, everything is done. And then you remain with real participants. So that's my own strategy to resolve a lot of these issues, and that's basically solve some of those concerns. And I think reviewers so far are quite happy about it. And I don't think they have a problem with this strategy.
I think also a benefit of that is that the bonus might actually be charged at the lower commission rate. So, Empirical has maybe 20% and 40%. Is it the case of the bonus? I thought the bonus was 20%.
I don't think so.
Okay.